Now, after we define series and we discuss how to test for convergence of series, now we reach the very important part of calculus 2, is how to represent a function by a power series. That is very important topic. We will start today the first step in that direction. What is that? The meaning of power series first. Okay, what is the meaning of power series when a power series is convergent? That's our target in this talk. So what does it mean, a power series first? Then, when it is convergent, that will be done in this talk, and the definition says a power series centered at x equal to a is defined by this, is a series of the following form. So it is a series written like this, n equal to 0 up to infinity, that is c sub n x minus a to the power n. Now, which is actually of the form c0, if you open it, if you expand it, at n equal to 0, this will be c0, this is x minus a to the power 0, which is 1. So that is c0 plus c1 x minus a plus c2 x minus a square plus. So it has a similar form of a polynomial, but this is continuous forever. So it is indefinitely. I mean, it is infinite series, in other words. Okay. Now, x is the variable. So x is a variable. What are the cn's here? Cn's are constants. So these are called the coefficients of the series. And of course, a here is called the center of the series. So we say this power series is centered at a. Why it's called centered at a? That will be clear when we discuss the convergence of the series. Okay. A special case of that, if you choose a to be specifically equal to 0, substituting for a equal to 0, we got the following shape, cn x to the power n, and that is just c0 plus c1x plus c2x squared, etc. So we call this one a power series centered at 0. Fine. The question is this. Question. When this series or this type of series is convergent. When it is convergent, when this series is convergent, the answer will be simple here. The answer, when this series makes sense, when it is convergence, what are the values of x for which this series is convergent? That's the question. The answer, use the ratio test. The ratio test will help you to find the answer. So what is the ratio test? That's why we said the ratio test is maybe considered one of the most important tests we have done in series discussion. So what is the ratio test? The ratio test says always you need to calculate the limit as n goes to infinity of absolute value of an plus 1 over an. If this limit less than 1, then we have absolute convergence. If it is greater than 1, we have divergence. If it is equal to 1, something else needs to be done because this test is inconclusive. We have no conclusion. So let us see if really this test will help us to find the answer. So we need to discuss this quantity. This is equal to what? Is it less than 1? Is it greater than 1? Is it equal to 1? Then we can answer the question. So let us, talk about some exercises. Example number 1, for instance, says for what values of x is the series given by this series given by summation. Here we have, okay, I'm just choosing this, n equal to 0 up to infinity. That is n factorial x to the power n. N factorial x to the power n. Okay, before we start, when this is, of course, what? Convergent. When this one, convergent. When this is convergent, for what values of x is the series convergent? So this is the question. When it is convergent. Fine. Before I start, I comment on the definition here that always, at least we have one point of convergence at the center. If x equal to a, always we have convergence because this will be destroyed. It will be just denominated to 0. It will be just 0. If you substitute here x equal to 0, for instance, the center, then always this is convergent series. So we have convergence at 0 at the center. But the question is, how far we can go from the center? We have convergent at one point, which is the center. How far we can go? Okay, this will give us the values of x where this series is convergent. Let us apply the ratio test as recommended here. What is the ratio test? The ratio test says evaluate the limit as n goes to infinity, absolute value of an plus 1 divided by an. An is the nth term given here. Look, this is a power series. This is a power series. These are the coefficients of the power series, and this series is centered at 0 by definition. Now, let us calculate this expression now. This is equal to what? Limit as n goes to infinity. Now, we need the absolute value here. I replace n by n plus 1, so that is n plus 1 factorial. This is what we have like this. We have x to the power n plus 1 divided by an, which is the nth term, n factorial, x to the power n. Now let us simplify this. This is equal to what? Now deleting x to the power n, I mean simplifying, so this is x to the n plus 1, I get x only. I have n factorial, n plus 1 factorial, that will give me n plus 1, because what is n plus 1 factorial? It is n plus 1 times n factorial. Cancelling, simplifying, we have the following. Now I have x here, this is n goes to infinity, I can take it outside, so that will give me absolute value of x times the limit as n goes to infinity of what it remains here is just n plus 1. And clearly here as n goes to infinity, regardless of what is x, the value here is going to infinity. So what can we say here? Infinity is greater than 1, isn't it? Infinity is greater than 1. The ratio test says if the limit is greater than 1, regardless if it is infinity, greater than 1 or infinity, then the series is divergent. So what does it mean now? According to the ratio test, this series is divergent for any x except x equal to 0. Because if x equal to 0, we said that is guaranteed by definition that we have convergence here. But if x is not equal to 0, then if x is not equal to 0, this goes to infinity. So I will say here to be precise, this is greater than, this is equal to infinity if what x is not equal to 0, to be precise. Now what is the conclusion? The conclusion that this series, by the ratio test, this series by the ratio test, okay, this series, the series is divergent for any x not equal to 0. Because if x is not equal to 0, then the limit of this is greater than 1. If it is greater than 1, the ratio test says the series is divergent. So what is the conclusion then? By this, so the conclusion says, so the series is convergent only if what? Only if x equal to 0. So it's convergent only at the center. Okay, fine. Let us see another exercise about this. When a power series is convergent. That's very interesting and important question always. When a power series is convergent, that is one nice question. Another one, does a function have a representation as a power series? A third one is how to find this representation. Today we'll answer one of them only, which is when a power series is convergent. Let us see another exercise. Another exercise here, that is, do the same, example number 2, do the same for this. For what values of x, I will repeat this, what values of x for which the series given by summation of, we have here n equal to 1 up to infinity, x minus 3 to the power n divided by n. This is very interesting exercise, okay? Why? Because we will use our previous knowledge in testing for convergence together with the ratio test. Fine. When this is convergent, this is the question. When this one is convergent, okay, for what values of x does it converge? So what should we do? As usual, we need to apply, as recommended here, the ratio test. So the ratio test says you need to start writing limit as, or calculating the limit as n goes to infinity of a n plus 1 divided by what? A n. That's what we have to calculate. This is a n, all of this. So applying the test, we have limit as n goes to infinity, and we have absolute value. What is a n plus 1? Replacing n by n plus 1. So we got x minus 3 to the power n plus 1 divided by n plus 1 multiplied by. Actually, it is divided by an, but multiplying, I will take the reciprocal. So I have here n, and here I have x minus 3 all to the power n, and I need to close the absolute value now. After simplifying this expression, this will give me, this is equal to, look, we have x minus 3 to the power n, x minus 3 to the power n plus 1. So x minus 3 will survive. So I have x minus 3 outside. I will take it. Then I have limit as n goes to infinity. Okay, I have n over n plus 1. No need for absolute value because these are positive. N plus 1. Okay, fine. What I did, I cancel x minus 3 to the power n with x minus 3 to the power n plus 1. It remains x minus 3 here. It remains x minus 3. So what do we have is absolute value of x minus 3 times the limit. What is the limit of that expression here as n goes to infinity? For sure, this goes to 1. So the final answer is absolute value of x minus 3. Now we should be careful here. Not yet we apply the ratio test. We didn't use the conclusion of the ratio test. What we did until now is just to calculate this limit, and it happened to be equal to absolute value of x minus 3. Now the ratio test says if this limit is strictly less than 1, we have absolute convergence. If it is greater than 1, divergent. If it is equal to 1, no conclusion. So let us see what will happen in these three cases. Okay, fine. Let me just write this conclusion and try to investigate what's happening if this limit is equal to 1. Okay, fine. So by the ratio test, we have what? By the ratio test, the series actually is not only convergent, it is absolutely convergent. Is absolutely convergent if what? If absolute value of x minus 3, which is the limit of an plus 1 over an, if this is less than 1. And divergent if absolute value of x minus 3 is greater than 1. It says nothing about the case if this quantity is equal to 1. Let us see the picture now. X minus 3, absolute value of x minus 3 less than 1, it means x minus 3 will be between minus 1 and 1. This is the algebraic solution of the inequality here. You are adding 3, so this will be 4. Adding 3 here, this will be what? Will be 2. So what do we have is this. We have, this is the real line. And we have here, let us say, this is the center, which is called 3. According to this, I can move up to 4, up to 2. I am sure now, inside this region here, inside this region, in the interior of this region, I have absolute convergence guaranteed by the ratio test. Not only this, I am sure also we have divergent here. So we have divergent to the right of 4. We have also divergent here. And we have absolute convergence between 2 and 4. The problem is this. what happened exactly, or what's happening exactly at x equal to 2, and what's happening exactly at x equal to 4. I will say the ratio test gives no conclusion. Why? If x equal to 2, this limit is 2 minus 3 is minus 1, with the absolute value will be 1. So the test is inconclusive. At x equal to 4 again, this is equal to 1. Since it is equal to 1, the test says I give you nothing. So what should we do now? Okay, as far as we did, we know that it is divergent outside. According to what we have done here, it's divergent outside. It's convergent inside. But these 2 points need to be investigated separately. So what should we do? I will take them a line like this, x equal to 2. And I will study this case, what's happening. Then I will take x equal to 4, study it also, and conclude something about the series. So let's come here and discuss the case where x equal to 2. 2 minus 3 is minus 1. Minus 1 to the n over n. So that is the series obtained if we substitute x equal to 2. N equal to 1 up to infinity. We got this. Minus 1 to the n over n, which is what? Convergent. Now, this is very famous. We did it before. It's convergent by alternating series test. This is an alternating series. Pn is 1 over n decreasing and goes to 0 as n goes to infinity. So it's convergent by alternating series test. I will say it is and I will leave the justification for you because we did this example before. It's alternating series, which is convergent. So this is convergent at x equal to 2. I mean, the series is convergent at x equal to 2 because the obtained series here is convergent by alternating series test. What about x equal to 4? What kind of series we got if we have substituted in x equal to 4? This is n equal to 1 up to infinity. And let us take 4 and substitute and see what will be gained. If we substitute x equal to 4 here, this will be 4 minus 3. And 4 minus 3 is 1. 1 to the power n is 1. 1 over n. So the series obtained is 1 over n. And this is again a very famous series which is called the harmonic series or a p series with p equal to 1. The conclusion is this series is divergent. This is divergent. Okay, fine. Now we are done with the exercise then. We are done with the exercise. Let's come back to this discussion we made before. So what do we have here? Okay, the ratio test says this series is convergent from 3 to 4, from 2 to 3. It's convergent absolutely. It's divergent here. I will write D for divergence and C for convergence. It's convergent inside. But these 2 points we discussed here says it is also convergent at x equal to 2. So what do we have here? We will close it from here. This is a point of convergence. Yes, between 2 and 4, open, it's absolutely convergent. But at x equal to 2, it's only convergent. And it is divergent outside. So what is the final answer? The series is convergent for all x belong to the interval 2 to 4 open. So it's closed from 2 and open from 4. With the help of the alternating series and the p series or the integral test, we got the answer for the convergence. Now, why they call it centered at 3? From where the word centered came here. You can see the interval here. We have an interval centered at 3. So the interval of convergence is centered at 3. So this is one reason why they call this series as a power series centered at 3. The 3 point here, or the point which is equal to 3, is the center of the interval of convergence. Okay. Now the first exercise, we had a series which is divergent all the way except at a point, which is the center. And the second one here, we get a series which is convergent in an interval. Okay, this is an interval, 2 to 3, 2 to 4, sorry. It is an interval at the end. And we will have now a third one and see at the end what kind of series we have. So a third example here. Now let us see a third example where we have the question says find the domain of the Bessel function of order 0. This is one of the special functions we have in mathematics. It is defined in terms of series, in terms of a power series actually, and we are trying to see where this series is convergent. That's what we mean by finding the domain of the series. Domain of the series or domain of the function is defined to be the set of all values of x for which the series is convergent. Again, we will apply the ratio test. So I will apply the ratio test. So I need to calculate the limit as n goes to infinity of absolute value of an plus 1 all over an, and that is equal to limit as n goes to infinity. Okay, fine. What I need to do is to take an absolute value. So that is absolute value. I will forget about the minus 1 because it will be killed by the absolute value. I have here what? X to the power, that is 2n plus 2. Why? Because I am replacing n by n plus 1. So it will be 2n plus 2. Fine. Divided by the same thing you do for this. 2 to the power 2n plus 2. And that is n plus 1 factorial. This is inside the factorial. All squared. So this is all squared. Fine. Multiplied by. It is actually divided by this. But multiplied, I will take the reciprocal now. So this is 2 to the power 2n. This is n factorial, all squared, all over x to the power 2n inside the absolute value. Okay, fine. Let us see the simplification will give us what? This is limit. N goes to infinity. Okay. If you simplify, you can cancel x to the power 2n with x to the power 2n. So we have x squared is remaining. The same thing you do for 2 to the power 2n plus 2, 2 to the power 2n. This will be cancelled out. So what we have here is just, if you allow me, I can take this outside. It will be just x squared over 4 outside. Then we have the limit as n goes to infinity. And then simplifying the factorial with the factorial here, I have n plus 1 all squared. We'll cancel with n factorial all squared. And what is remaining is just 1 over n plus 1 all squared. Why? Because you can rewrite n factorial, n plus 1 factorial always as n plus 1 times n factorial. With the squared, it will be n plus 1 squared, n factorial squared. N factorial squared will be cancelled with n factorial squared. Now the question is, what is the value of the limit here as n goes to infinity? The answer is 0, regardless of what is x. It's always 0. X is a real number. A real number times 0, so it is 0. Okay, fine. But you know that 0 always less than 1. So it means for any value of x here, the limit an plus 1 over an is less than 1. So by the ratio test, it says this series is absolutely convergent for any x. So what are the values of x for which the series makes sense? All values of x. So this has an open domain. So I will say the domain, let me just write this. Domain of the Bessel function of order 0, the domain of this function is minus infinity to infinity. We gain this by the ratio test. The series is convergent by the ratio. Let me write the conclusion here. Okay. The ratio test says that since the limit is equal to 0, which is less than 1, so by the ratio test, by the ratio test, the function, the Bessel function g0 of x is convergent for all real numbers x. It's convergent everywhere, in other words. Now let us summarize what we did. We had an exercise, the first one, which is convergent only at a certain point, which is the center. Divergent everywhere. The second one is convergent only inside a specific interval. And the third one is convergent everywhere for any x, absolutely convergent. The question is, do we have something else? And the following theorem will answer this question and will say, no, you have only three possibilities. Either the series will converge only at the center, or it will converge everywhere, or it will converge over a specific interval. That interval will be called the interval of convergence. And the length from the center to one endpoint is called the radius of convergence. I will summarize this in the following theorem. Now, this nice theorem will summarize the cases we did. It says, if you are given a power series, then for sure there will be only three possibilities. What are the three possibilities? You may have a series that converges only at the center, like the first example we did. It's divergent everywhere except at the center. Or the series converges for all x, like the Bessel function we have. It's convergent for all values of x from minus infinity to infinity. More interesting, you may have, there is a positive number r such that the series converge only if, not only if absolute value of x minus a less than r. So I repeat this. There is a positive number r such that the series converges if absolute value of x minus a less than r and diverges if absolute value of x minus a greater than r. Okay. What do you call this r? This r is called the radius of convergence. Now, a second point. The interval that consists of all values of x for which the series converges is called the interval of convergence. That is very interesting. The third one is these two interesting points here. What's happening at x equal to a plus or minus r? At the endpoints, everything is possible. You may have both points will be points of convergence. You may have both of them are points of divergence. You may have one of them is a point of convergence and the second point is a point of divergence. Because this is exactly what we mean by this. We have, this is the real line, okay? We have a center here called A. Then we have a point here called A plus R. We can move always this distance, which is called the radius of convergence. And here we have A minus R. Okay, this theorem says always you have divergence here. Always you have divergence here. Always, okay, let me erase this. We have convergence inside. Okay, between A minus R and A plus R, we are sure that we have convergence. The question is, what's happening exactly at x equal to A minus R? And exactly at x equal to a plus r, what's happening here? I will say these 2 points, let me write it this way. These 2 points need to be investigated. These 2 points need to be tested alone. Because these 2 points are points where the limit of the ratio test is equal to 1. No conclusion. Everything is possible. So we need to discuss these points separately as we did in the second example, if you remember, and as what we will do in the following 2 exercises. Let us see what will happen now if a question says, like example number 4, example number 5 says, find the radius of convergence and the interval of convergence of the following series, of the series given by this, of the series given by this, which is given by summation here. We have n equal to whatever it is, 0 to infinity. This is what we have. And this is minus 3 to the power n. And that is x to the power n divided by square root of n plus 1. So this is a power series again centered at 0, whose coefficients are given by this expression, minus 3 to the n over radical n plus 1, we need to study now the radius and interval of convergence of the given power series. So according to this theorem we have only 3 possibilities. Let us see which one of them is here and how to find the radius and interval of convergence. I try to make some space to write, so please, okay, we need to do that. So let us try to use the ratio test again. Applying the ratio test, by using the ratio test, by using the ratio test, we get the following. Okay, we got the what? If we have the ratio test says always you need to evaluate, you need to calculate the limit as n goes to infinity of absolute value of an plus 1 over an, and then study the case where this is less than 1, this is greater than 1. Fine. Let us do that for this specific series. So this is the limit, okay? As n goes to infinity, I have absolute value. I will replace n by n plus 1. So with the absolute value, I forget about the minus. It will not affect anything here. So this is 3 to the n plus 1. If you allow me, I will take out the minus sign. And that is x to the power n plus 1, okay? Divided by, this is radical of n plus 2, fine. Multiplied by, it is actually divided by an. So it is the reciprocal of the quotient we have. So that is 3 to the n, and that is x to the n will be in the denominator, and we have radical of n plus 1. That is inside the absolute value. Okay, fine. This is equal to what? Let us simplify now. I will delete x to the n. With this, x will remain. 3 to the n will be cancelled out. So what do we have here is just 3 upstairs. So what do we have? We have 3 absolute value of x. I'm taking it outside the limit, and then I have the limit as n goes to infinity. What do we have inside here? We have just radical of n plus 1 over n plus 2. Now as n goes to infinity, clearly this goes to what? This goes to 1, and radical 1 is 1. So the final answer is 3 absolute value of x. Okay, that is exactly the limit of an plus 1 divided by an. Now the ratio test says, if this is less than 1, we have convergence. If it is greater than 1, we have divergence. So what does it mean now? Let me write it this way. So this is the limit. So by the ratio test, we have the series by the ratio test, the series is absolutely convergent whenever we have 3 absolute value of x is less than 1, and not only this, divergent if we have what? 3 absolute value of x is greater than 1. That is what the ratio test says. Okay, let us look for the convergence. So we need to solve this. So it is convergent. Actually, it is absolutely convergence if absolute value of x is less than 1 over 3. Okay? So I'm dividing by 3 only to get absolute value of x less than or equal to 1 over 3. Now, we can gain from here the radius of convergence. According to the theorem we did, this implies our radius of convergence r is equal to 1/3. And that's exactly what we will have. We have an interval. This is the real line. We have 0, which is the center. We have 1 over 3 here, and we have minus 1 over 3 here, and we are sure that this is divergent. It is divergent here. It's convergent inside. But we are not sure about x equal to minus 1/3 and about x equal to 1/3, because these 2 points, if we substitute here in the limit, then 1 over 3 times 3 will be 1, and minus 1 over 3 inside absolute value again will give me 1 over 3 times it will be 1. So the test is inconclusive. So what should we do? To conclude this discussion, I need to go and study the case where x equal to 1/3 as well as the case where x equal to minus 1/3. That will be done, and then we can conclude about the interval of convergence. We have the radius of convergence. We are looking for the interval of convergence. So what we need to add here, okay, just to be symmetric here, let us go to the same distance. This is what we have, something like this. Let us say approximately. So this is x equal to minus 1/3. This is x equal to 1/3. Okay, let us see what happened if x equal to, let us start with minus 1/3, minus 1/3. What do we have? What kind of series we have? N equal to 0 up to infinity. Fine, let's go and substitute minus 1/3. Minus 1/3 to the power n times minus 3 to the power n. They will cancel each other. Look here. Minus 3 to the power n times minus 1/3 to the power n. This is minus 3 times minus 1/3 all to the power n. And clearly this is equal to 1. So that will give 1 only. So that is 1 over square root of n plus 1. What can we say about this series? What can we say about the series here? The series here is divergent. Why is divergent? You can easily show that by shifting only the index. This is n equal to 1 up to infinity, 1 over radical n. This is a p series. Divergent, I will say this way if you like, divergent p series. Why it's divergent p series? Because p is equal to 1/2, which is less than 1. We discussed this one as a result of the integral test, and we said whenever we have a p series, p less than 1, it is divergent. So this is divergent. So this point is not a point of convergence. Okay, what about x equal to 1/3? If we substitute x equal to 1/3, let us see what do we got here. If we substitute 1/3, okay, let's erase our calculation here. Okay, 1/3 to the power n, 1/3 to the power n, and this is minus 3 to the power n. So what we have here is minus 1 to the n, minus 1 to the n, all over square root of n plus 1. Okay, let me say some words about this. I will say this is convergent. Why it is convergent? This is the question. Why it is convergent? Why? Why? Why it is convergent? This is an alternating series whose bn terms 1 over radical n plus 1 is decreasing and goes to 0. So by alternating series test, this one is convergent. So the conclusion says this is convergent by alternating series test. Of course, you need to write the details. Why the alternating series test says it is convergent, and simply what you need to do is just to take the bn's here. The bn's are given by the bn is equal to what? 1 over radical n plus 1. You need to check two conditions. The first one, bn plus 1, it's clearly less than or equal to bn for all n greater than or equal to 1, so it's decreasing. And the second one, what is the limit as n goes to infinity of bn, it's equal to 0. So that's why the alternating series test says this one is convergent. Fine. What should we do now? We go back to our case. Now we are done with these 2 points, and we found that this point is not a point of convergence, but the other point is a point of convergence. So we are sure now, not only this, together with 1/3, then we have what we call the interval of convergence. So what is the interval of convergence? Interval of convergence. It is equal to minus 1/3 open, but 1/3 closed. I will comment in this interval. Inside the interval, not only we have convergence, we have absolute convergence. At x equal to 1/3, we have only convergence. At x equal to minus 1/3, we have divergence. Outside, for sure, we have divergence. Okay. Is it always that one of them will be included, the other one is excluded? I will say no. Other exercises, you may have both of them are excluded. You may have one of them is included, like this example, you may have both of them are included. I will give you an exercise and we will see that both boundary points will be excluded. Okay, and that will be exercise number 5. So we have now plenty of exercises about this. Okay, I will repeat the same story here. So this is example number 5. I will say example number 5 is exactly has the same statement as example number 4. We are looking for the radius of convergence, interval of convergence. Do the same for the series which is given by this. It's given by what? It's given by n equal to 0 up to infinity, and that is n times x plus 2 to the power n divided by, this is divided by 3 to the power n plus 1. Okay? This is what we have. Is this series, what kind of points, or what are the points for which the series is convergent? So find the interval of convergence, find the radius of convergence. That's simply the question. Again and again, I will write limit as n goes to infinity. I'm calculating this ratio, an plus 1 over an, and then I take the limit as n goes to infinity. So this is equal to the limit as n goes to infinity. Now what do we have here is just as the routine work we did before. It is n plus 1, okay, and that is x plus 2 to the power n plus 1 divided by 3 to the power n plus 2 multiplied by 3 to the power n plus 1 all over, that is n times x plus 2 to the power n inside the absolute value. Fine. Simplifying and writing the final form after cancelling common factors. Okay, I will delete this with that one. I will have 3. I have x plus 2 to the power n with this one. I have x plus 2 upstairs. So what do we have here is just absolute value of x plus 2 divided by 3. What it remains here is the limit as n goes to 1 over n, which is equal to 1. So that is what? That is the limit here. Now, according to the ratio test, this series is absolutely convergent if this limit is less than 1. So let us study the case where this limit is less than 1. So we have convergence. And if it is greater than 1, for sure, it will be what? It will be divergence. Okay. So this implies if this quantity, which is x plus 2 over 3, if this is less than 1, the series if this is less than 1, the series is absolutely convergent by the ratio test, by the ratio test. Okay, this is what we have. So let us discuss this. Absolute value of x plus 2 less than or over 3 less than 1 implies that what? That is absolute value of x plus 2 is less than 3. So what is the conclusion now for the radius of convergence? This implies from here we can read the radius of convergence. The radius of convergence R will be equal to 3. Okay. So it means from -2, I can move 3 units to the right, 3 units to the left. I am still inside the interval of convergence. Solving this inequality, we got the following solution. Okay, x plus 2 is bounded between -3 and 3. Adding -2, so this will be x3 minus 2 is 1. And here we have -5. Okay, so we have the center is at -2. That is a power series centered at -2. We can go up to 1. So this is -1, this is 0, and this is 1. So we can stop here. And then we can go 3 units to the other side. So this is -3, -4, -5. This is -5. Okay, that's equal to 1. And we are sure now we have convergence inside. And we have divergence outside by the ratio test. Now, what's happening exactly at x equal to -5 and at x equal to 1? These 2 points need to be taken and investigated separately. Because, you know, at x equal to -5, this is equal to 1. At x equal to 1, this limit is equal to 1. So we have no conclusion by the ratio test. Okay, let us study these two cases and then conclude about the interval of convergence. Let us do that here. That is the case where we have x equal to minus 5. If x equal to minus 5, what will happen here? If x equal to minus 5, we have the following series, n equal to 0 up to infinity. Okay, let's go back to the series and substitute x equal to minus 5. We have here minus 5 plus 2. Minus 5 plus 2 is minus 3. Minus 3 to the power n over 3 to the n. Forget about the plus 1 here. This is 3 to the n times 3. So what do we have? We have minus 1 to the n times n divided by 3. What can we say about this series? Clearly, this series is divergent. Why it is divergent? I will say, since the limit as n goes to infinity of the nth term, minus 1 to the n over 3 does not exist. Since this one does not exist, the series is divergent by divergence test. Okay, the divergent test says the series is divergent. Okay, since we are talking about a specific test, let us give it a capital letter here. So it is divergent by divergence test. Okay, that's one thing. A second point of interest is x equal to 1. So let us see at x equal to 1, what do we have? X equal to 1 will lead us to the following series, n equal to, this is 0 to infinity. And I substitute x equal to 1 here. Again, 1 plus 2 will be 3. 3 to the n will cancel with the 3 to the n. You have n over 3. And again, this series is divergent. Why it is divergent? For the same reason. It is divergent because if you take the limit of the nth term, this would go to infinity, which is not equal to 0. Yani the limit does not exist. So it means the limit does not exist. So the series is divergent. Of course, by divergence test. By divergence test, or what they call the nth term test of divergence, the same. So this is divergent, that's divergent. So what is the conclusion then? It means the interval, so the interval of convergence I is equal to what? We exclude minus 5, we exclude 1, so the interval of convergence is simply minus 5 and 1. So this is another exercise where 2 points, the 2 boundary points are excluded. We have some exercise, one endpoint is included, the other one is excluded. You may have another example where both points are included. So we say everything is possible at the boundary points. This is how to test a power series for convergence. So we define what is the meaning of power series, then what is the meaning of the center of the series, what is the meaning of interval of convergence and radius of convergence, and how to find these two things, interval and radius of convergence. This is what we have for power series. Okay, next we will see how to apply this discussion to represent a function in terms of a power series.